Good afternoon. Sorry for the interruption. We are trying to get connected with a set of groups in the western part of India who were not able to hear us properly, and in some cases they were not connected to the NKN even though they had a connection. But now that we have been able to address a large number of them, we are proceeding with the first lecture, which is on the introduction to algorithms. So, this session will be on the overview of algorithm design, and I hope that you have seen the lecture corresponding to this which we showed earlier. As we have mentioned in the beginning of this program, that this algorithm design course tries to approach the design of algorithms from the point of view of engaging the student into a process of discovery. And there are several phases of this algorithm design problem, and the first phase of algorithm design at any point in time is related to be able to accurately specify the problem. So, in our case, we are trying to develop, as we have mentioned in our original lectures, a process, whether there is a process for a beginner to learn algorithm design. However, in spite of the process, before we go to the process, the first and the most important thing for any algorithm designer to do is to be able to specify the problem accurately. The problem specification in itself, if it is done ambiguously, will obviously lead to a wrong algorithm being designed. And the problem specification requires specification of the input, the output, and the various constraints that must be put in place. And we shall discuss in the whole process as the first step how to specify. The second step of any algorithm that you design, and the second requirement for any algorithm that you design, firstly the algorithm must terminate, it must be functionally correct, and then you look at efficiency, user interface, implementation, error handling and documentation. And if you have seen the lectures that we had uploaded in the workshop, then you will see that the overall process that we looked at considers these four basic steps. The first is initial solution. How do we prepare an initial solution? And this initial solution consists of preparing a solution which encompasses many possibilities. It is just not a single solution. Then you explore the overall space of possibilities of this initial solution and analyze it for termination, correctness, and then for efficiency. And based on that analysis, as we shall see, we are able to decide on the parameters and make a final choice, and from that we will get the data structuring. So, design analysis of algorithms consists of algorithms and data structures and their final implementation. All these concepts are fine, but the best way for us to actually take a student through is to be able to teach the student through examples. So, examples are going to be the most important way in which we will take students through. And the most important thing about any example is to take a student through one example in multiple ways, to show that the problem can be approached in multiple ways with the same philosophy. So, we will now proceed into our next step of algorithm design, and the first thing that you would like to do is to be able to unambiguously specify the problem. And at any point in time, the specification of the problem is the key to design of the algorithm. and we shall see how. So, coming to the problem, let us look at one example. This example we have seen even in our coordinators workshop, and I would recommend that an example like this is to be looked at as the first example for teaching any student algorithm design. So, let us look at the problem of finding the smallest of n numbers. So, what we would like to specify is a problem of smallest of n integers for the time being. The first thing that a student should do in specification, so we are looking at specification. The first thing that the student should learn is to specify the inputs. Now, here let us look at what options we have. The first thing we can say is the input I is a set S of integers, S consisting of elements S1, S2, S3 to Sn, and we can say it is a set of integers. Now, is this accurate? The first question somebody will ask is, if this were accurate, a set by definition does not have duplicate elements. So, what about duplicates? So, if we use a set definition to assume that duplicate elements do not exist, then obviously the set definition is not an accurate definition in this case. So, in this case, an accurate definition would, in computer science language, not typically in set language, but here when we design algorithms we use some other terminologies. So, we would use what is called a list. A list is a set, but it can have multiple elements of the same type. So, instead of a set definition, we will use a list L of n elements, L1, L2, L3 or Ln. So, this is a list, there is no particular ordering on the inputs. The inputs is not defined by any order, because we are not saying that there is an order initially, we are just saying that there is a list of inputs. And then we have to again clearly mention that this list Li is an element of integers, if we are looking at integers. If we are looking at anything else, if we are looking at positive numbers, then we have to say positive numbers and so on. And then we could also say that these are all positive numbers, so each Li is greater than 0. The next, once we come to the inputs, then next what we have to specify is the output. And in order to specify the output, here again, what would the output be? Would it be a set? Would it be a list? None of them actually. The output here is a sequence, because it is not only a list, but it is an ordered list. That means that there is a first element, there is a second element, there is a third element, there is a fourth element, etc. So, we say that the output O is a sequence, not a list, of O1, O2, O3, I am sorry, this output here would be a single element. If we are to produce only the smallest of n integers, the output here would not be a single, would be only a single element, but if we are to sort it, then it would be a sequence of elements. So, first let us look at the smallest problem that we have taken into account. So, the output is a single element x, and what is the property of x? I am keeping this part here. When we discuss sorting, we will come back to this. The output is a single element of x, and what is the property? That x is an element of the list L, and x is such that it is less than equal to Li for all Li in L. So, in order to find the smallest element, it does not only have to be less than equal to all Li, it also has to be a member of L. Now, let us come to the question of specifying sorting. When we want to specify the problem of sorting, let us come back. The input again is a list L, and the output is a sequence, is an ordered list, and there are 2-3 properties on that ordered list. One, OI is always less than or equal to OJ if I is less than equal to j. That is the first property, that we are now sorting it in ascending order. The second property is that every OI has a 1-to-1 correspondence with some L in L. That is, if I have got n elements in the initial list L, then in the output sequence also I will have n elements, and every element will map to a unique element in L. That means, you cannot have some extra elements, you cannot have some less elements, and you cannot have some duplicate elements. So, here again the input, output and the relationship between the input and output is to be specified very, very accurately. Let us take another example. Let us take an example where we are saying subarray sum. The problem is defined as follows. There is an input is an array of elements. So, it is an array or a sequence of elements. So, it is an array A which is sequenced as A1, A2 to AN, and this is a sequence, it is ordered, there is an ordering amongst them, but that does not mean it is sorted or in any other order. So, for example, A could be 5, 8, minus 3, 2, 6, minus 5, 1. So, here again I allow positive and negative integers, and my output says that I want some sub array. I want some sub array, that is a sub array. I first define a sub array. A sub array is any sequence from any element I to any element j within the array. For example, if I take the sub array from the second element to the fourth element, then it consists of the sub array 8, minus 3, 2. So, there are how many subarrays? For every pair that you can take from a small element to a large element, there are forms a subarray. So, for every I and every j such that I is less than equal to j forms a subarray. Now, every subarray has a sum. The sum of this subarray is 7. Our output is find that subarray whose sum is largest amongst all possible subarrays. So, here there can be order of n squared subarrays. It is very easy for you to see that there can be order of n squared subarrays, and for each subarray there is a sum, and we want to find that subarray whose sum is the largest, and we want to find the value of that sum. So, here is another problem where specifying the problem would require you to specify an input sequence which allows indexing of the elements. Then you would have to define what is a subarray, and then you have to define the sum of that subarray, and then you would have to define the maximum of that sum of that subarray. So, similarly, when we come to any specification, then you must try and specify the problem in a clear, unambiguous manner, and the most important thing when you specify, you give an example. You give an example to explain the specification, especially when you have got multiple cases. For example, if you are finding the maximum of n numbers and you want to consider both positive and negative numbers, then your example should contain positive and negative numbers. So, the specification of a problem must contain the inputs, the outputs, and the conditions or constraints given. Here are 4 examples that we have highlighted here: finding the smallest of n numbers, sorting both of them we did. I would request you to try and specify during your discussion session and any other session how you would accurately specify finding the median of a set of numbers. So, the median of a set of numbers is that number for which there are equal number of elements which are less than equal to it and greater than equal to it. So, how would you specify the median of a set of numbers? So, that is very important for you to see that the median could be a single element, could be a multiple elements, because if there are even number of elements, then how would you define a median? Let us look at what are the nitty-gritties of specification. Let us look at the problem a little carefully in more details. We are to find median. So, let us take an example. We are to find median, and so let us take an example. Suppose in an example our set of elements is 5, 2, 11, 6, 7. Then here we can clearly see that 6 is the median, because 2 and 5 are less than 6 and 11 and 7 are greater than 6. On the other hand, if we had taken 5, 2, 11 and 6, then what would we define as median? If we choose a single element as median, then we would find it difficult to find equal number of elements on both sides. So, here we have to clearly define what is median here. One option sorry, that we could take is we could define a pair of elements as median. For example, we could say the median is 5 and 6 such that 2 is less than both of them and 11 is greater than both of them. Again, on the other hand, if we instead of a set, if we had 5, 6, 6, 11, then again 6 itself alone is the median, because it is a duplicate element even though there are even number of elements. So, what I am saying here is that when you define and specify the problem, so that the algorithm's output is properly defined, therefore, here you have to list out all the cases in the input output specification. Let us take the fourth example of string matching. We know about a pattern and a string. A pattern is a text pattern. For example, in the newspaper or in the net, suppose I take a text file, that whole text file is a string. Now, in that text file, maybe I am searching for a pattern, and I am searching for a pattern, maybe it is called algorithms. I am searching for the word algorithms in that whole text file. So, how will I define the pattern matching problem in saying that how many matches of algorithm are there in the string or in that whole text? The word algorithm is easy. On the other hand, if I take a non-trivial case, so suppose I have a string S. So, I am talking about the pattern matching problem. Suppose I have a string S, it is called my course on algorithms taught us design of algorithms. Here there are two clear matches for the pattern P algorithms. And I would say that there are two matches, and how would I define the problem? I would look at this whole string as a single string where all the gaps would also be considered as blanks. This could be a blank, this could be a new line, whatever. And I am looking for this word algorithms there. How many matches of this word in this single string exist? But then the problem, when you define the problem, you need to be a little more careful, because you may have what are called overlapping patterns. Which means that suppose I defined a string S as A, B, C, D, A, B, A, B, A, B, A, and my pattern as A, B, A, then if you look at this string, then here is a match, here is a match, and here is a match, and three matches are overlapping. So, when you define the problem, you must be very clear whether you are looking at the pattern matching problem with overlapping strings or without overlapping strings, because the solution with overlapping will be 3, whereas the solution without overlapping allowed would be 2. So, I would request that all of you concentrate a little more on looking at these 4-5 problems and try to find a clear unambiguous input output specification. So, any problem that is given to you, the first step in algorithm design would be an unambiguous input output specification. The second and more important thing is that you will actually get to solve real life problems. You are not going to get problems which are classical textbook problems to solve. And when you start mapping these real life problems, then you need to look at these problems in a more modeling approach. So, how are we going to look at problems and we are going to model them? Let us look at these few problems. The first problem that is listed here is to find the root in a map. So, the general problem would be, so let us see how we are going to do the modeling. So, the example is root in a map. So, the input actually given to you is a map. There will be some cities in the map. These cities will have latitude, longitude, and or any other coordinate, and between two cities there will be a distance. That means, this distance identifies whether there is a direct route between these two cities and what is the distance in this direct route. Your output, another input that you will get is a start city and a destination city. And from the start city and the destination, given the start city and the destination city, your problem is, output is, find the shortest length path from the start city S to the destination city D. Certain constraints will be obvious to you. These distances are all positive integer, positive numbers. So, all distances are positive. And the shortest length path will be defined as a sequence of cities where the first element in that sequence is the city S, the last element in that sequence is the city D, and there may be some intermediate cities I1, I2, I3, etc. And a path is, the length of the path is the sum of the distances on this set of on this sequence of cities between the intermediate cities. So, this is the problem given to you. How are we going to model this problem? The easiest way to model this problem is to form a matrix, a two-dimensional matrix. Suppose we have 6 cities C1, C2, C3, C4, C5, C6. And each element of that matrix will contain a value which is the distance. So, the element from C1 to C2, if it is 3, then it means that the distance between C1 and C2 in that direct route is 3. Obviously, all diagonal elements are going to be 0. So, the mapping or the modeling of this problem could be a matrix of positive integers. Only the diagonal elements can be 0 and the rest of the elements will be some positive distance of a city to city mapping. So, you can take the problem and convert it to a matrix form or a 2-dimensional array form, or another way of looking at it is called a graph. A graph, as we all know, G equal to V E, where V is a set of vertices and E is a set of edges or vertex pairs, and the graph could be defined by a set of 6 vertices in this case, and between any 2 vertices there will be an edge if there is some distance between them. If there is no route between, say, city C4 and C5, there is no direct route between C4 and C5, then this matrix will contain infinity. So, if this is C1, this is C2, this is C3, this is C4, this is C5 and this is C6. Then if there is no route between C4 and C5, then the matrix will contain infinity between C4 and C5 and there will be no edge in this graph between C4 and C5. Then again you will have to check from the input specification whether this distance between the cities is symmetric or not. That is, if the distance between I to j is the same as the distance between j to I. Now, somebody may ask, why will that not be the case? It may differ from problem to problem. If you are looking at the distance as the road distance, then obviously this distance will be symmetric between a city C I and C j will be the same as C j and C I. But if you are looking at flight distance, then there may be a flight from Calcutta to Lucknow. There may be a flight from Calcutta to Lucknow, but that does not have, there is no direct flight from Calcutta to Lucknow. All flights from Calcutta to Lucknow go via Patna. On the other hand, all flights from Lucknow actually come from Lucknow to Calcutta and then go to Patna. So, the flight sequence may be that the same aircraft starts from Lucknow, comes to Calcutta, goes to Patna and goes back to Lucknow. So, you will have a distance between Lucknow and Calcutta, direct distance, but you will not have any direct distance from between Calcutta and Lucknow, because you, on the other hand, you will have a direct distance between Lucknow and Patna and you will have a direct distance, between Calcutta and Patna and a direct distance between Patna and Lucknow. So, there may be symmetricity, there may not be. Let us take other examples. Let us take another example called the crypt arithmetic problem. All of you may have solved puzzles. So, a puzzle, a crypt arithmetic puzzle is given as something like this: break plus and we would like to know what are the values of this. Obviously, this r and this r have the same value, and whatever be the value of g, r plus g must be the same value as s. So, given an crypt arithmetic problem like this, we would like to know the values of these a, b, c, a, b, r, e, a, k, g. What are the possible values? At least can we have one solution? So, how are we going to model this problem? So, we can specify this problem saying that what this problem is about, and the specification of this problem would say that we first need to specify this. See, the input to this problem, input is one string S1, one string S2, the operator O, and the output string S3. And what I really need to know is, other than these, there will be an alphabet set A consisting of A, B, R, E, K, G, etc., etc. So, there is this alphabet string, and I would like to know what are the values of these alphabets, these elements, such that the arithmetic matches with this. So, in order to do this, how will I model this problem? I leave it for you to examine how we are going to model this problem. You can try it at the discussion session. Similarly, you are given a set of telephone poles, you want to know the minimum wire to connect all the telephone poles, or you are given a timetable, and all of us who are teachers do timetable scheduling. Similarly, we have the stamp selection problem, the pumping water in the city. We have given this as a discussion problem itself. You have a set of pipelines, you have a set of pumps, and these pumps have certain capacity to pump water, and you would like to know what is the, given the pumps, given the pipeline, given the capacity, what is the maximum amount of water that can be taken into the city. And I have listed several problems, and for each of these problems we will have to do a modeling. And in order to do a modeling of these problems, we will see that in other than logical expressions, we have to use things like matrices, graphs, constraint satisfactions, integer linear programming. So, there are a variety of techniques that we need to use to map it into problems. Among them, set theory, logical expressions, matrices, use of constraints, use of optimization, and in a large scale of computer science algorithms, we will notice graphs forms one of the most important frameworks for modeling. Now, we come to what we tried to talk about, and if you have watched the video lectures, about what is the approach to algorithm design. We have said that in order to design an algorithm, instead of just telling them what the algorithm is, the first thing that you would like to tell the students for teaching any problem or any algorithm is to first tell them you design the algorithm yourself. So, the first thing that you would like to tell anybody in the algorithm design approach, as a teacher, in any course that you are trying to teach in algorithms design, for a teacher, the first thing that you would like to tell the students is try and design the algorithm. Let us take an example. Let us ask them to find the maximum and minimum of n numbers. We have done this example in the video. So, ask them to find the maximum and minimum of n numbers. So, let us take this example through again, and we will see how we are going to approach people to do the initial problem definition. So, of n positive integers. And as soon as you give the problem to the students, we all know what they are going to do, and we should not disturb them as to what they are trying to do. So, what we will notice, and as teachers, the first thing that when we prepare for a class is to try and anticipate what they are going to do. When you are going to do anything, it is important for us to try and anticipate, and you will see that there will be several things. The naive ones will find the maximum and then find the minimum. Some others will try to do it together. So, once you try to do it together, how will they do it together? Those who are good at programming would read two elements. So, they would do what? Read two elements, assign larger to max and smaller to min, and then they would read one element at a time and update this max and min value as the two variables that they have and proceed till the end. So, then they would read an element at a time and update max and min. These are the typical ways one who would find the maximum and then the minimum, and the other would do this. At this stage, it is important to first highlight the issue of complexity. How many comparisons are we doing for doing this? In the first case, we know that finding the maximum of n numbers, in the first case, finding the maximum of n numbers requires n minus 1 steps, and then finding the minimum of that, if you remove the maximum, would require n minus 2 steps. So, it would be about 2n minus 3 comparisons, a ballpark estimate. The second approach, they would require one comparison to do this. They would read two elements, they would require one comparison to assign max and min, and then when they come here, then in the worst case at every step, how many comparisons would they take? What would they have to do? They would have to read an element, they would have to take the element x, compare it with max. If x is greater than max, then obviously they would assign x to max, and whatever is the current max would be removed. On the other hand, if x was less than min, they would assign x to min. So, in the worst case, they would have to do both the comparisons, because x would probably neither be greater than max nor be less than min. So, they would still require at every other step till the end, in the worst case of other than the first step, which would require one comparison, for the rest n minus 2 elements, they would require two comparisons, which would again take them to somewhere close to 2n minus 3. At this point in time, it would be important to now bring in the concept of exploration of the design space. And it would be important to see whether we can improve this strategy a little. So, what we would try to tell them to do? We would like to tell them that, look, instead of reading one element at a time, could you read more than one element at a time? Could you do something? So, if you read two elements at a time and compared them, so instead of reading one element at a time, you read two elements at a time. And if you read two elements at a time and compare them, you have a larger and a smaller. Then you compare the larger with max and the smaller with min, which means that you are doing 3 comparisons for every 2 elements. You are doing 3 comparisons for every 2 elements. So, let us go back and look at this a little more carefully. What you are saying is, instead of this, read 2 elements at a time. Yeah, they cannot see this, right. So, we are saying read 2 elements at a time, and then, so you have read 2 elements P and Q, compare P and Q to get min temp and max temp. One comparison to find which is the temporary minimum and maximum, and then you compare max temp with max and min temp with min. So, in 3 comparisons, you are going to tackle 2 elements. So, now how does your complexity arise? Just to keep everything on the same piece of paper, previously we are doing 1 plus n minus 2 into 2, but now what will be the comparison? In the new case, I am writing it here, the comparison will be 1 plus n by 2 into 3. Obviously, for odd and even you will start doing a little bit of difference. 1 plus n by 2 into 3, which effectively tells you that you are going to end up doing approximately 3n by 2 plus some constant comparisons, plus one number of comparisons, which is dramatically less than the 2n minus 3, because you have got 3n by 2. Now, once you said I could do 2 at a time, somebody will say, why can't I do 3 at a time, 4 at a time? Is there a general way of looking at this? Is there a general way of looking at this? So, how can I reach a general way of looking at this? So, as you proceed on this example, we have done the example of max earlier, we have done the example of max and second max earlier in the video lectures. I purposely did the example of max and min, though we have discussed it before in the video lectures, but I did it in a different way. Now, as soon as you have these multiple alternatives, that brings us to the idea of the core topic of this methodology of algorithm design of initial solution by recursive definition. If you have watched the video lectures, then you may have noticed how we did it for maximum, minimum and sorting and various other things. We particularly did not do it for this example. So, let us see what is our approach. Our input is a list L of integers. Let us assume they are all positive integers for the time being. So, what is our, when we do recursion, what do we do? Split L into L1, L2, two disjoint lists of L1 of L. The third step, find the max 1 and max 2 is equal to max min L1. This is our program for max min L. Then find max 2, sorry, max 1 min 1. Min 2 of max min L2. And then we require two comparisons, one to find the maximum of these two. So, max is equal to largest of max 1 and max 2, and min is equal to min 1 min smallest of min 1 min 2, and we return. Obviously, there will be base conditions. The base conditions will be here. The base conditions will be captured here. If the size of L is 1, then that same element is both max 1 and max 2. You do not need any comparisons. And if the size of L is 2, then in one comparison you can find max 1 and max 2. Since you can do this, here is a recursive definition which allows you to split into any order. Now, the special case that we looked at, after the third case that we looked at, the second case that we looked at was actually splitting it as one element at a time, whereas the third case that we looked at was splitting it as two elements at a time. So, the question comes as to what is this whole recursive definition going to give us. This recursive definition, as we have seen, will give us a recursion tree. So, if this is a set of 6 elements, or let us take a set of 8 elements, 5, 7, 1, 3, 4, 2, 11, 15. This is a set of 8 elements. Now, we could split it at many ways. We could split it as 1 n minus 1, 2 n minus 2, in the middle, wherever we could split it. And if we suppose we split it here, then it would be 5, 7, 1, 3, 4, 2, 11, 15. Recursively, the max and min of this would be found as 7, min would be 1 and max would be 7. Recursively, here the min would be 2 and the max would be 15. And the min of these two would be the min of this, which is 1, and the max of these two would be the max of this, which is 15. This is what this definition says. The next thing that we need to do is analyze this definition. The analysis of such definitions come from what are known as recursive equations. So, if we suppose we always split it in the middle and assume that there are 2 to the power n elements, then suppose we split it in the middle. So, T n would be 2 T n by 2 plus how many comparisons? 2 comparisons. This is if n is greater than 2. This would be 1 if n is equal to 2, and this would be 0 if n is equal to 1. So, the next question would come as to if I did it this way, what would be the answer? The other I could do is T n is equal to T n minus 2 plus T 2 plus 2, which would come up as, I am breaking it up as n minus 2 into 2. So, it would T n minus 2 plus T 2 is how much? 1. T 2 is known to be 1. So, it would be 3. So, this is one. Base conditions remain same for both. This is the other. We can easily see from here that this recursion turns out to be 3 by 2 n plus 1. What does this turn out to be? I leave this as an exercise for you to find out. On the other hand, if we had split it as T n is equal to T n minus 1 plus T 1 plus 2, then we would end up as T 1 is 0. So, T n minus 1 plus 2, this would end up as what? 2 n minus 1, or this would lead to 2 n minus something, because T 1 would be 0. So, we can easily see that there are 3 splits that we have examined: 1 n minus 1, 2 n minus 2, half half. I have left the half half for you to do as an exercise. So, the next step from the recursive definition comes is how we are going to actually analyze the algorithm. And we have seen that if we do the 2 n minus 2, which we had actually seen when we had done it that way, we will get this. Is there a more general answer to this? I will leave this as part of the discussion. Is there a more general answer to this? In order to go to a more general answer, the approach that we take is build up the recursion tree. So, if you had say 8 elements and we build it up this way, we did 2, 6, 2 is a base condition, 2, 4, 2, 2. Then we look at the cost involved. The cost of doing 2 elements is 1, here 1, here 1, here 1. Cost of doing multiple elements is how much? 2, as our definition says. Our definition says in the recursive condition you have to do 2 comparisons after you come out of the recursion. So, the cost of any intermediate node is 2. Whereas, the cost of a leaf node depends. So, on the other hand, suppose we had done 8 elements, suppose we had split it as 3, 5, 1, 2, 3, 2, 1, 2. Previously, we had 3 internal nodes and 4 leaf nodes. We now have 1, 2, 3, 4, 5 leaf nodes and 4 internal nodes. Each of the internal nodes is of cost 2. And the leaf nodes, if it is 1 is cost 0, if it is 2 is cost 1. If you add this up, the total complexity is the cost of the values at the nodes. And you can easily see that this cost of this is going to be much less than the cost of this. And from here, you can take it down that a more general way of analyzing this algorithm is to look at the recursion tree and the cost at the nodes. And then after all this exercise is done, then it would be very interesting to then point out or tell them a nice story about how this could easily be done without all these things. What you could easily say is that anybody who is good at designing competitions, knockout competitions, if he has to find the winner and the loser or find the maximum and the minimum, would simply say that you first develop what is called a tournament. This comparison tree of various kinds forms what is called a tournament. A tournament in which 2 players play with each other and then play with the champions play with each other, where the comparison tree of finding the maximum of n numbers is a normal tournament. Whereas, the comparison of here is like a doubles match, and I will explain these tournament structures in a little more details. And then you can easily say that what I would do is, I would find a tournament in which the largest of n numbers is found. The largest of n numbers can be found by playing people in a tournament. And we have explained this tournament example in our original lectures in details. And then we say that in a tournament, after the first round is played, there will be half winners and half losers after the first round is played. The smallest number can only be found among the losers. And that is how we have shown there that it can be done, because n minus 1 comparisons is required to find the maximum. And if you compare only with the losers, then compare with half of them, then for that half you can find the winners. So, bringing this overall idea is the objective is to try and introduce the basic mechanism for our approach. Our approach is to get the initial solution by a recursive definition, then to analyze the recursive definition through recurrence relations and the asymptotic complexity as we just showed, and in details in the other lectures these are shown, and then open up the search space to look at the recursion tree, and then look at how you will make that optimal choice in the divide and conquer to find what is the recursion tree that we need. And then once we have identified that, then we will have to now look at how we are going to traverse this recursion tree. The traversal of this recursion tree and the memorization of the information across traversal of this recursion tree will be your main approach for algorithm design and the process that we are trying to evolve. So, the approach to design of algorithms is to demonstrate each of these by examples. We have shown the largest of n integers, the largest and the smallest as I just said. Then we have seen a very unique example of the largest and the second largest. And we build that up by building up what was called that tournament comparison structure. If you watch the videos of those lectures, especially the first lecture which we have discussed, and I do not want to repeat it here, then you will see how we build up that tournament structure. And once we build up that tournament structure, we found that finding the largest, the next largest can all be done in log n complexity. After you have found the single tournament structure, then you can find the others in log n complexity. And therefore, there was a unique way of finding the largest and the second largest. The largest can be found in order n time and the next largest can be found in order log n time. I do not want to repeat this here, please watch those video of that first lecture and you will get those. Next we will come to other examples where we will show how we are going to demonstrate it with various other aspects of algorithm design in terms of memorization, traversal, pruning, greedy, etc., etc. And it is also important that when we teach this first course on algorithm design, try to make yourself as well as the students write down this generic recursive definition. The generic recursive definition will produce this solution space, and it is through this solution space that people will try to work it out. So, I have listed out these 10-11 problems. I will request all of you to start writing out the recursive definitions for these problems, and we will start discussing these issues as we go ahead. I think 1 hour is over, right? So, we will stop here, break for about 5-10 minutes and then start taking questions. Yeah, that is all right.